Alright, so how many leaves as a function of n? You might think that's a strange question because we did just in fact answer it on the previous slide. It's n factorial. What is the height of a tree as a function of k? And again, we answered this one on the previous slide. The height is how many comparisons we had to make. So that's going to be k. What is the maximum number of leaves? Or maybe I should call that the maximum depth of it, because the height is going to be k plus 1 actually. What is the maximum number of leaves in a depth k binary tree? Well, your easiest method here is to draw out different values for k and the number of leaves. So let's say we have a depth k, so let's say the depth of a tree is 0, so we would have 1 leaf. Let's say we have a depth 2, so k is equal to 2 tree. What's the maximum number of leaves? Well, I can have a leaf for every parent node, so I'm going to have 2. And then how about the next level? So level 3, I can have 1 leaf, 2 leaf, 3 leaf, 4 leaves. So what's a general function for that? It's going to be 2 to the k. And of course somehow I put a 3 here instead of 2 because I can't count. And then one more level, we should end up with 2 to the third, which is 8. So how do I get that? 1, 2, 3, 4, 5, 6, 7, and 8. So the maximum number of leaves in a depth k binary tree is 2 to the k. Alright, so our next question is, what is the minimum height of a binary tree with n factorial leaves? I have n factorial because we know that's how many different permutations are there. What's the minimum height of our decision tree, essentially, above, is another way to say that. So the minimum height of the decision tree. Well, this is going to be the reverse operation of what we just did. So if I have 8 leaves, what's the minimum height? It's going backwards to these other values. So my minimum height is, instead of going 2 to the k, I'm going to have log base 2. And instead of k, I'm going to have n factorial leaves, because I was talking about k up here, n factorial here. So I'm going to have log of n factorial. That's the minimum height of a tree with n factorial leaves. Alright, so what we want to compare are these two quantities. The number of leaves as a function of n, and the maximum number of leaves in a depth k tree. So in fact, which one of these is bigger? The number of leaves with n factorial, the number of leaves with n factorial numbers, input numbers, or the maximum number of leaves in a tree of height k, depth k. I need to make sure I'm more consistent on my slides, sorry for that. Well, your answer here is to look at the decision tree we had before. So here I had n factorial leaves, and if you notice, not all of them are at the maximum depth of the tree. So n factorial would correspond to a tree that could look like this. And if you notice, there is not a leaf here. That one's missing. That missing blue one would not be missing if I have the maximum number of leaves with the height k. I would have all possible leaves present. So this one on the right is greater than the one on the left. Again, the one on the left is n factorial, the one on the right is 2 to the k. Okay, so the reason for that is we might not have a full tree in the case of n factorial. So we have that n factorial is less than or equal to 2 to the k, where that's the number of leaves with n numbers, and that's the maximum number of leaves with a depth k or k comparisons of those n numbers. Whenever you have an exponent, it's always nice to start by getting the exponent out front, because I want to solve this for k. So I'm going to take the natural log of both sides, and the reason I take the natural log and not the log base 2 will be apparent here as we go forward. So I've got k times natural log of 2 on the right hand side, and this thing here is a constant, so I'll just replace that with a constant, call it c1, and that's our quantity so far. That's our lower bound. and on the right hand side we have the number of comparisons. So I could say that k is always greater than or equal to 1 over c1 times the natural log of n factorial, and we could be done there. We're not going to stop there though, because this quantity of log of n factorial is not very intuitive. It's kind of hard to understand. We've got a function here that doesn't grow very fast, and n factorial, a function that grows about as fast as any function you could think of. There are functions that grow faster, I want to make that clear, but the n factorial is sort of one of our practical, we don't have many practical algorithms that grow faster than n factorial. So in comes the Stirling's approximation to save the day here. It turns out that n factorial is equal to n log n minus n plus big O of n log n. So that's what we'll replace on the left-hand side. The first step I'm going to do is I'm just going to get rid of the negative n. So I'm going to use an intermediate step to say that this quantity is greater than what I have on the left-hand side because I no longer have the negative n quantity. Alright, next I'm going to take this big O of n log n, and I'm going to put that into terms of like an asymptotic notation. So I'm going to multiply that by a constant c2 and say that big O of n log n is less than or equal to c2 times n log n. And after I do that, I've got c2 n log n and n log n, and I'll just combine those two together and I'll call that c3. So c3 is really just c2 plus 1. And then I'll divide both sides by c1. So I have c3 and c, all constants on one side, and I'll just regroup those together and create a new constant and call it c4. And that's what we have. So we have k is big omega of n log n. And remember, we can always change the base if we'd like to. Change a base is just multiplying by a constant factor. So now we've proved that the number of comparisons is lower bounded. We have to do at least big O of n log n comparisons to go from an unsorted array down to one of these sorted sequences. K is the number of comparisons to go from the root of the tree down to the base of the tree.